Hello everyone, my name is Aaron. I'm the speaker and I'm from University of Cambridge. I'm really glad to be here today to present my work, Rapid Model Architecture Adaptation for Meta Learning. This is a piece of joint work with Zitong from Chinese Academy of Sciences, Ilya and Robert, both from Cambridge here, and Nick Lowe from Microsoft Research, New England. So in this talk, I'll probably first give you an introduction, then I will describe the proposed method, and finally I will show you an evaluation of the proposed method. So when we're talking about neural networks today, only a small portion of people are thinking of the deployment of those networks. If we think carefully about how we are deploying networks today, we realize we're deploying networks for different tasks. We're deploying networks on different hardware systems. And also, quite importantly, we're deploying those networks with different latency and memory constraints. And if we think carefully of what is a good representative case for this, is probably, in our opinion, the few-shot learning system. This system follows exactly this many task, many device setup. If we consider deployment of neural network models on different user devices on key applications such as facial recognition, then the identification of each user's face is basically considered as a new task. You have people using different versions or different types of mobile phones, meaning they have different hardware systems. And also on a single hardware system, for example, my phone, there might be 2 or 3 apps that's running the same task, but with different constraints. Probably one specific app will require this neural network model to have a better latency, and the other app probably requires the neural network model to be smaller. So this describes a deployment scenario where we have a number of tasks as a letter T. We have different hardware systems. Then in here we used edge, and also different constraints. So the 3 parameter here gives us a very large design space. It's basically T times H times C. And as the diagram here is illustrating, what happens in today's life is there might be some engineers that's looking at this problem saying, hey, we will perform this architecture engineering for different task hardware and constraint combinations. And most of the time, that means he or she will have to retrain the model or have to fine-tune the model T times H times C times. Or otherwise, it will just not have the optimal accuracy. So we focus exactly on this many task, many device setup. And now I'm going to introduce the method, but before doing that, I think it's a good idea if we do a quick revision on MAML, because our method is heavily inspired by MAML. So equation 1 here states the objective of basically the MAML algorithm. And the full name of MAML is Model Agnostic Meta Learning. It's basically a training framework that helps us to learn on a set of training tasks. So here I'm presenting it as with a fixed network architecture, represented as alpha hat. So the key idea is that we learn on a set of training tasks, and the finally learned weights, or people also call them meta parameters, can be useful and then be quickly adapted to any unseen tasks. So this is also a very cool conceptual name, as some people call it. This is the concept of having learning to learn. In our case, we basically want to modify the MAML algorithm. Then we want to state the objective of learning on the training tasks with a set of possible architectures A. So as equation 2 here is illustrating you, we have to sample every time an alpha from a set of possible architectures A. And in other words, we basically added this architecture sampling, and we make sure that each candidate in the architecture search space will be warmed up using this MAML framework. So this explains part of our method's name, where we call this meta-NUS. The hardware-aware part here comes to this equation 3. This equation states the architecture search process. We use a genetic algorithm to obtain optimal architecture alpha that is conditioned by a given hardware constraint. So after now the MAML training on the set of training tasks, we can adapt to a new task based on this hardware-specific constraint, and we're also providing the new task with optimal weights and also optimal network architecture. So to quickly summarize what I've just described, we now have 3 key phases in the algorithm. We have a SuperNet pre-training phase, which is pretty much the modified MAML algorithm I just described to you. Then in the second phase, we'll have this layer-wise profiling training. It's basically building a layer-wise profiler so that we can profile the runtime of different network architectures on real devices. Then later, we'll have this device-aware task-specific deployment. So after again our profiling information of how fast specific combination of the network would run on our device, we know which ones we can deploy based on doing the genetic algorithm. So in this case, given the task and the hardware platform, we will deploy with not only the optimal weights, but also the optimal hardware architecture, and this hardware architecture will fall inside the given runtime constraint. Another interesting observation we've made during designing this algorithm is that existing NUS has a relatively restricted search space because most of them only optimize for a single task. And if you imagine a set of tasks that you have to optimize, and some of those tasks can be super challenging, while some of the other tasks can be very easy. The diversity in those tasks encourages us to use network models that are both super big so that they can tackle the challenging tasks, and also the very small network architectures so that they can be easily adapted to simpler tasks. So that we introduced 2 methods to cope with this problem. The first method is global expansion. This allows the NUS algorithm to globally expand or shrink the number of channels of all of the layers. The second method we have is called adaptive number of layers. This will allow the NUS to use an arbitrary number of layers, and the network is then able to already stop using only a few number of layers from the big SuperNet. So these 2 methods together will allow us to construct super small networks for easy tasks and giant networks for tasks that are super challenging. Now we're going to look at the evaluation. In our paper, we considered different hardware systems, as this is a way for us to demonstrate we are proposing a hardware-aware algorithm. So we considered some representative systems across the system stack. On the cloud side, we considered the NVIDIA GeForce GPU. As a representative of a mid-end CPU, we used the Intel CPU. And for mobile and IoT CPUs, we use different versions of Raspberry Pi. And for ASIC accelerators, we picked Iris, and we used a simulator for Iris, which is called ScaleSim. The details of the specs of the CPUs and also how we operated with the simulator is in our paper. And the data sets, we consider three very popular benchmarks in the few-shot learning domain. Those are OmniGlot, Mini ImageNet, and FC100. So this is the results on Mini ImageNet, and the horizontal axis here shows you the inference latency on different hardware systems. The y-axis here indicates the accuracy. So in general, our NAS method performs a lot better than both manually designed and other NAS baselines. More results like this can be found in our paper, and it's also important to consider search efficiency when we're talking about NAS algorithms. So if we consider comparing the search complexity with N tasks, H hardware platforms, and C number of hardware constraints, and we present here a search time estimated for a deployment scenario with 500 tasks and 10 hardware constraint pairs. And as expected, the proposed H meta-NAS shows a better search time because it has a lower search complexity, and the search time is around 40 GPU hours for us. In summary, in this talk, I showed you that network architecture search is a suitable method for large-scale deployments with varying hardware systems and hardware constraints. In this talk, I give an example in the many task and device learning scenario that is few-shots learning. And a lot of details of our evaluations and the proposed method is in our paper. I will invite you to read it if you're interested. And I'm also here to answer any questions if you have any. Thank you for your time.